Welcome to another class of CS360, and um, this um, in this lecture we will cover some closure properties for context-free languages. So, okay, so a few closure properties that we've seen for regular languages. Some of them also hold for context-free languages. So let's just go through them. So the first is union. So if A and B are context-free, so that means they have context-free grammars. Then what does that mean that A union B is context-free? So this is true. Why? Well, because we know that A and B are context-free. So they have context-free grammars. Let's say GA and GB. Okay, and those have some rules, like SA goes to something, and we have some rules. Let's write them in this box. And the GB also has a start variable SB that goes to something and has some other rules. We'll put all those rules in this box. And so what we can do is we can kind of merge the boxes, kind of take the union of both. And then we'll have a new start variable S. We'll say that S can go to either SA or SB. Okay. S can go to either SA or SB. And in addition, we will put all the box, like the box, that box for GA, we'll put it down here. And in addition, we will also put the box for SB, for GB. So that will be this box here. So we will merge all the rules and we make sure that none of the variable names overlap. Okay, so we can change the variable names first to make sure there's no overlap in variable names, and then we can kind of merge all the rules together. And we get a new context-free grammar. This new context-free grammar has a start variable S, and the path that we can take in it will always either go through SA or through SB. Through SA, we get a string in the language A. Through SB, we get a string in the language B. And so from S, we can get any string in A union B, and also only the strings in A union B. Okay, so it's pretty simple. So a similar trick can give us the language AB. So AB is also context-free. And this is basically the same, except instead of SA or SB, we're going to have S goes to SA, SB, okay, next to each other. So SA will turn into some string in A, SB will turn into some string in B, so S will turn into a concatenation of some string in A and some string in B, and that turns out the set of all such concatenations is exactly the set AB. Okay, so great. So this shows AB is context-free. And we can, in fact, do the same thing with A star. So A star is context-free. Okay. Why is that? Well, this time we don't have B, so we're not going to include those rules for SB. Okay. But instead, we will do this. Okay, we will say that S can become SAS or epsilon. Okay, so first of all, remember that A star always contains epsilon for any language A. Okay, so this is fine. And also, if you take any finite number of strings in A and concatenate them together, that should be an A star. And here you can see that we can basically do the derivation. S goes to SA, S goes to SA, SA, S. And then we can do this any number of times we want, and then use the epsilon rule, and then we'll get some number of SAs followed by epsilon. Okay, so we can get any number of K of SAs, and then each of these will turn into a potentially different string in A. And so we can get a finite concatenation of strings in A. And A star is indeed the set of all finite concatenations of strings in A. So we exactly get A star. Okay, and this is not a formal proof, it's just a sketch, but it should convince you of why this construction should work for giving us a context-free grammar for A star if we had a context-free grammar for A. Okay, so now if the class of context-free languages is closed under union, concatenation, and star, and if also we have, if it's also true that each of the kind of base case languages, like if the languages, the empty language, the language containing only the empty string, and then the languages containing only C for each C and sigma. If each of these is context-free, and they are, it's pretty easy to construct context-free grammars for those. Then just it immediately follows that every regular language is context-free, because every regular language can be constructed by starting from these base case languages and then applying union, concatenation, and star in some combination. Okay, that's how we define regular languages, in fact. Okay, so every regular language does have a context-free grammar, and we can construct this context-free grammar basically by starting from the base case context-free grammars for these guys, for these guys down here, and then using the union concatenation of star to build up more and more complicated context-free grammars. Okay. Okay, so that kind of basic, but it's so that it shows, it finally formally proves that every regular language is context-free. Now let's do a different proof. Let's do one in terms of DFAs. So right, remember that a DFA looks like you know, is it a transition diagram for a DFA, right? Let's just draw one. Whatever. We can have a loop here when we see a 0, and then we can go here when we see a 1, let's say. Okay, and then we can, let's say we do something like this. Okay, so this will recognize, the CFL will recognize all the strings that have an odd number of ones. Okay, and if we name the states, like let's name this Q0 and Q1. If we name the states, then we can now, construct a context-free grammar that's based on this DFA. So how would that work? Well, we'll have one variable for each state. So we will have basically, let's call it x0 and x1, where x0 corresponds to q0 and x1 corresponds to q1. And for each transition, we will have a rule. So remember that the transition means we read a 0 from the input, but in context-free grammar, we're trying to generate the input. So what we'll do is we will kind of generate that 0 instead of reading a 0. So if we're looking at this rule here, for example, okay, that rule says we read a 0, but in a context-free grammar, we're trying to generate the input. So we will generate a 0 if we're trying to mimic that rule. So for that rule, we will write x0 goes to 0x0. Okay, and then for the other rules, like for example for this rule here, then we go x0 goes to 1x1, right? Because so we moved from state q0 to state q1. So here we'll move from the variable x0 to the variable x1. Okay, and there will always be one variable in this context-free grammar. We'll be generating. There's always going to be exactly one variable on the right-hand side. Or none. So okay, so let's just keep writing down all the rules here. So we get from x1 we can go either to x1 when we see a 0, so that would be this rule, or we can go back to q0 when we see a 1, so that's this rule. Okay, and then finally the accept state. The accept state, we're allowed to stop reading a string. So if we want to stop generating the string, we sort of want to end up here in the accept state. So the accept state, q1 is the only accept state, so we will have the rule x1 goes to epsilon for the accept state, which basically tells us that we are allowed to stop generating the string now. And then finally, the start variable will be x0, because q0 is the start state. Okay, so the start variable is going to be x0. Okay, so so this is going to be a context-free grammar, and then you can see that it indeed generates all the strings that have an odd number of ones. So for example, like if you look at this string here, okay, so the transition, when this DFA reads the string, then it starts here, and then it loops when it sees a 0, loops when it sees a 0 again, goes here when it sees a 1, and then loops when it sees a 0, and then accepts because it read the whole string. And then to generate it, we kind of want to follow the same path. So we first use this transition here. So we'll start with x0, right? And then we go to 0x0, which is like looping on the first state. And then we loop again on the first state. So we get 0x0. Okay, and then we transition to x1, and we get 001x1. And then we loop on x1. So that gives us 001, 0x1. And then finally, we want to accept. So we want to use x1 goes to epsilon. Okay, so we generated the string. Okay, and you can kind of see that any accepting path can generate a string that corresponds to that path. And so you can convince yourself that this strategy can give you a context-free grammar for any DFA. Okay, so that's another proof. Okay, and so finally, an important closure property. Well, okay, so first of all, what is not true? It's not true that context-free grammars are closed under intersection. Okay, so A intersect B might not be context-free. Even if A and B are context-free. Our CFLs are context-free languages. Okay. But it turns out that if one of them is regular, then this intersection is context-free. Okay, so if A is a CFL, is a context-free language, and B is regular, then A intersect B is a CFL. So this is a theorem. Okay, so the proof of this is somewhat complicated. It is in the notes. The gist of it, though, okay, so we start with a context-free grammar for A. A is context-free language, so we need to start with a context-free grammar for A. So, you know, this will be this grammar GA, and it will have some rules like, let's put the rules in this box. Okay, so, and then we will start, B is regular. We need to use the fact that it's regular. So we don't just want a context-free grammar for B. We want to start with a DFA for B. So the DFA for B, let's call it like MB. It's this DFA for B. And, you know, it has all these states like Q0. And then, you know, it has all these, whatever. It has this transition diagram over here. Okay. Whatever. So it has all these transitions over here. Okay, so now we want to show that A intersect B is context-free, which means that we want to construct a context-free grammar for A intersect B. So we want to construct a context-free grammar G for A intersect B. We can also assume G is in Chomsky normal form. This is often an additional assumption that can be helpful. So it's nice to have. So we can assume that it has this nice form that minimizes epsilons, and each variable turns into exactly 2 variables or into an alphabet symbol. Okay, so we'll assume that. Why not? Okay, so then we want to create this context-free grammar G. So this is a little bit complicated. Basically, the way it works is we will have one variable for in G. Let's call it xpq. For each variable x that's in the variables for GA, for each x there, and then every p and q that are states. So they're in this set q of states. Okay, so for each 2 states and 1 variable, so for each triple of variable state, we have 1 variable in the new grammar. Okay, and the idea for this grammar is that it generates all the strings that are both generated by x in the old grammar GA and also cause the DFA to go from P to Q. Okay, that's roughly the idea, and then, you know, we just need to describe how you can kind of generate this variable from more such variables, basically. So what are the rules that this variable can transform into? And okay, so, well, we can look at what x can generate in the grammar here. So if x has a rule, x goes to yz. Well, the only rules that x can really have is either x goes to yz or x goes to c. We'll ignore the start variable that can go to epsilon for now. So in Chomsky normal form, you basically only have these two types of rules. So for the rule x goes to yz, then, you know, we can imagine we want to generate the strings that, so we sort of want something like this. So we want x goes to yz, but we also want that the string that's generated by y, when you concatenate it with the string that's going to be generated by this z, will cause the DFA to go from P to Q. Okay, so we will basically want that this will cause the DFA to go from P to P prime, and this will cause the DFA to go from P prime to Q. Then when we concatenate the strings together, it will cause the DFA to go from P to Q. Okay, and so we want to have this rule basically for every P prime. Okay, and for every such rule, x goes to yz. Okay, and similarly, if when we have the rule x goes to c, then we basically want to write x pq. We want to write this goes to c, but only if we only want to include this rule if basically delta of pc is q. So we only want to include this rule if from P in the DFA, when you see a C, you really go to Q. Okay, so in that case, then we want to include this rule. Okay, and so these rules should hopefully feel at least a little bit intuitive for why we're mimicking this property that this variable xpq generates exactly the strings that can be generated from x in the grammar GA, and also which cause the DFA to go exactly from P to Q. Okay, so this is what we're trying to do with the variable xpq, and as long as you remember that that's what we're trying to do with the variable xpq, then what the rules should be is sort of self-explanatory in terms of the rules of G, as well as the transitions of M. Okay, so for every rule of G, you can think which rules do I need to introduce, for every rule of GA, which rules do I need to introduce in G? And it's sort of self-explanatory from there. You have to introduce exactly these rules pretty much, plus some details with how you handle the start variable going to epsilon, and as well as what the start variable of G should be. Okay, so there's more details in the notes, but this is sort of the sketch of that proof. Okay, and the notes contain some other brief closure properties, including under prefixes and substrings and suffixes. Note that context-free grammars, context-free languages are not closed under intersection, and they're also not closed under complement. So those are two key closure properties that regular languages have, but context-free languages don't. So context-free languages don't have all the closure properties that regular languages do. And so this is important to remember. Even though there's more context-free languages, they're actually closed under fewer operations in a sense, or they're not closed under every operation under which regular languages are closed. Okay. All right. I'll see you next time.